Hi everyone, this is a Vapor tutorial on its particle renderer. You may be used to using Vapor on gridded Eulerian data, but Vapor also has a renderer dedicated to Lagrangian particle simulation data. And so in this tutorial, I'm going to step you guys through the features on basically how the particle renderer works. And then after that, we'll talk about the data structure, the netCDF structure of the data files that Vapor needs in order to read the particle simulation data. So we'll talk about how you guys can transform your particle data into a format that Vapor can read. So with all that being said, let's jump right in. I'll get out of my slideshow. And the first thing I'm going to do is show you guys how to generate an artificial synthetic particle dataset. So you can go ahead and start playing with the particle renderer in Vapor before transforming your own personal data into the correct format. And so after you've installed Vapor, right now I'm on OS X. If I look at my current working directory, on OS X, Vapor gets installed into my applications folder with these trailing subdirectories. It's a little bit more confusing than if you're on Windows or Linux. Whatever directory Vapor gets installed in, there's going to be an examples directory, which is where I am right now. So I believe if you're on Linux, it would be something like you would install Vapor into a Vapor directory, and then it would be in the, I think it's directly in the share folder right beneath the root installation directory, and same thing for Windows. So once you've navigated to this examples directory, you can do an ls there, and we have a bunch of scripts, NCL scripts, VDC examples, but what we're interested in is this generate example dcp.python script. And what DCP stands for is data collection particles. That's kind of Vapor's parlance for what a readable particle file is. So we're going to run generate example dcp.py, so python generate dcp.py, and I'm going to be missing one of the required modules, netCDF4. So since I don't have that, I can just do python -m pip install netCDF4. Okay, so now that we've installed netCDF4, we should be able to run our script, and it will quietly succeed. But if I do an ls on my current directory, I have 20 netCDF files that describe particle data that Vapor can read. If you like, you can go into generate example dcp.py. So if I take a peek at generate dcp.py, you can see here are the parameters for how it's generating these files. We have 200 particles initially in the data set. They are three-dimensional particles, and we are assigning them position values and also velocity values. And I'll talk a little bit more about that once we start talking about the data structure later. The last thing that you can change in this script, if you go to the very bottom, is basically we're generating one DCP file for each time step in the range up to 20. If you want more time steps, feel free to change this value to whatever you like, and have at it. So after configuring that the way you like it and running it, we can then load these DCP files into Vapor. So let's see, I'm going to close out my previous session and just for demonstration purposes, start from the beginning. So down here at the bottom of my screen, I have my V. I'll click on that. And then I'm going to go to my file menu and import data collection particles, DCP. And let's see. It's funny, OS X does not allow me to navigate to where my particles are put. So if I'm currently looking at my applications directory, and my particle files are within this directory called Vapor, and OS X in Finder right now doesn't let me explore into that directory. So what I'm going to do is I'm going to move particles, all the files, into my desktop. And then I will go to my desktop, and there they are. So I have my 20 files, click on open. Okay, and so like with any other dataset or renderer, we have our empty domain. Vapor is in its base state with no instantiated renderers. And so the first thing I'll do is instantiate my particle renderer by clicking on the new button, and then going over here and selecting the particle renderer. And you can tell the other renderers are not enabled because there is no grid for them to act upon. So the only renderers in a DCP dataset that can be used are images, models like STL files, and then finally our particle renderer. So I'll click OK on that. And the first thing I'll do is just go ahead and enable it. And here we can see our glyphs representing the position of each particle in the DCP dataset. I can play it forward in time, so if I click on this play button, you can see that they are moving around. They have again, they have a position value attributed to them, and they also have a velocity field attributed to them. If I look down here in my variables section, they're being colored according to a speed value, but I can also color them according to the different velocity parameters that are on that are designated to each particle. And then I have to select the field upon which they move through space. And so I just select the X, Y, and Z components of velocity, and that's what allows them to move through the scene like we just saw by animating forward and backwards. Another control in the variables tab is the stride parameter. And what this allows us to do is to sample the particles, so we don't necessarily have to render every single one in a data set. Some particle data sets have billions and billions of particles, and it would really slow the computer down to a crawl if you try to render something like that. And so in this data set, I have, I believe, 200 particles. And so if I do a stride of 200, that means I would be sampling one particle per 200, and we are only rendering one, and so on for other multiples. And then finally, if we want to see them all, we just do a stride of 1. The appearance tab works in the same way as the other renderers. We have our transfer function showing the distribution of our color mapped variable on the particle. So if I go back to variables again, we are coloring by speed, and in the appearance tab we have our data distribution of our speed variable, lowest value around 2.5, highest value roughly 30. You can go into your settings and load other color maps. These built-in presets are available for you if you like. And I think, I don't know, I like playing with this. I think a lot of these color maps look pretty cool with the particle renderer. But the point is that the particle renderer works in the same fashion that the other renderers in Vapor do, like the volume renderer, the slice renderer, etc. If I scroll down a little bit, there are options to change things like the size, the radius of my particles, so I can make them bigger or smaller, like individual points right here, very small, or I can make them huge, or if I want them even bigger, I can right-click on this and then designate a new maximum value. So if I want a radius of 250, I can change that there and just make them huge. So that's the kind of freedom of control that you guys can work with there. There's also an option to show the direction. So we have a, if I go back here, we have a velocity field, and there's also a position field that is kind of implicitly shown in the rendering. You don't really pick a position variable. It's something that you have to have in your data file. But one thing I can do is show the direction from the current position according to the velocity field. So if I click on this, we now have tubes being rendered, similar to what we do in the flow renderer. If I make these a little bit, yeah, I've lost the fidelity of my control. So I'm going to make the maximum back down to 25 and do something a little bit more reasonable like that for the thickness. And then the length can be controlled like so. And of course, this is the direction they are moving in is according to the X field, Y field, and Z field that we can select here, or alternatively in the variables tab. The last set of features in the appearance tab would be the lighting field. You can do things like control the ambient lighting that's being applied to the tubes or spheres, whichever you are rendering. If I turn that off, we go back to spheres. But yeah, there's just controls for the ambient, diffuse, specular lighting, and the shininess of the material. Geometry tab is basically the same thing as with other renderers. This just controls where you are sampling the data from, so I can select subsets and subregions by controlling the red bounding box that encapsulates my data. And lastly, there's the annotation tab, which allows me to turn on a color bar and give it labels like such. So I believe that's covered all of the GUI elements, roughly, of the particle renderer. The next thing that I need to address is the data format, because this DCP format, I believe, was kind of specialized by NOAA, but I'm not sure how widely it's used. And so if I clear out of that and I go to, let's see, I think I put my particles on my desktop. So if I cd onto my desktop, do ls, yep, there's my particle files. So what I'm going to do is on ncdump-h on particles with an s 000.nc pipe less. So this is the basic structure of our particle file. For Vapor to read particle data, it's required that we have at least, well, explicitly these three dimensions. There is P, which is the number of particles in the data set at the current time step. There is T, or time, which similar to NetCDF parlance, you can define it as unlimited or 1 if you're looking at the current file. Again, this can be either T or lowercase time. As long as that variable, capital T or lowercase time, exists in the file, Vapor will be able to read it, as long as it, of course, also has P, and then also this axis dimension that tells us, what dimensionality these particles exist in. You could have a two-dimensional particle simulation, but the script that we used earlier generates 3D particles, which I think is the common use case. Of course, we have a coordinate variable for time with a units attribute. I think that's following the CF conventions, and so if you don't have a units attribute and a coordinate variable for time, Vapor will probably choke. The position of the particles is required. This is an explicit variable that is a function of time, the number of particles, and the axis. And so if I do a, let's see, if I go over here to my desktop and I do an ncdump-v for position on particles 000.nc, we can see that the position of each particle is given as a triplet of values on the x, y, and z axes. And so this would be the position for particle at index number 1. There's only one time step per file. That's a requirement. You can't have multiple time steps for NetCDF files for the particle renderer, I believe. And so these are all position values for the current time step, and the particle number associates with the first three values according to the axis dimension, so axis 0, 1, and 2. Velocity is a kind of similar concept. We can do the same thing with velocity, and we will get similar values, but I guess the point I'm trying to make is that Vapor is relying on this position variable to be there in order to draw the particles at their point in space. Velocity and speed are not required. That's kind of just ancillary data that can be used to do things like show the direction of the particles, like we saw earlier. So if I do a ncdump-v on velocity, we're going to see velocity values for each axis in a similar way that we saw with position. Speed is different, though, because it's a scalar. There is no axis attributed to it, and so we're just going to see a list of values that pertain to the particle index that corresponds to those values. So if we go speed, here is just a list: particle 1 speed, particle 2 speed, and etc. And so those are basically the requirements. As long as you can get your particle data into a structure like this, where we have a number of particles that are indexed, a single time step per file, and either a two-dimensional or three-dimensional axis dimension, as well as a time coordinate variable with a units attribute, and a position variable, then you will be able to get your particle data into Vapor. And I know that doesn't all sound like the easiest thing in the world, but that's kind of like the nature of NetCDF and data standards. If you guys have any trouble, though, you can come ask us for help on our forum. Whoops, let me find a web browser here. Let's see, discourse, vapor.discourse.group. And you can feel free to ask us any questions you have here, or provide us some of your sample data and we can help you convert it into something that Vapor can read. So yeah, I hope that explains everything in a sufficient enough way. Thanks for watching and have a nice day.